project description has been released. I mean, if you look here, you see that the group project here, yeah, and then the project description is here, okay? And so far now we have 31 groups. So I think some groups you form it by yourself, but then some groups because nobody take a lead, so I just put, you know, like randomly. So please check your name here and your student number, and if it's not correct, please email me. Okay, but this is the group, and because we have 93 students, so we have 31 groups evenly, yeah, and then we have a lab test today and tomorrow. Okay, so that is more or less everything you need to know. So any question before we move to the new topic? So the new topic is about quadrature. So quadrature is more or less just numerical integration. Okay, and we will study two types of quadratures. One is Newton-Cotes rules, and another one is Gaussian rule. You see, I mean, the name of Newton is everywhere. So before you saw question.
Yeah. What does the material go out to for the lab test?
Before this one.
Like before today?
Yes. Not today. Okay. So is it clear now? Yeah. So everything, including nonlinear equation. Yeah. But excluding today. Yeah. Okay. So numerical integration. So essentially, so before we go to the general formula, let me ask you a simple question. Yeah. So what is the integration? So suppose you want to compute integral of So suppose you want to compute the integrals of something simple, like x squared, y equal x squared, from 0 to 2. Yeah? So integral of x squared dx from 0 to 2. Okay? Then how do you do it? Huh? How do you do it? Well, you just use the rules of calculus, right? Yeah? But now, suppose I ask you to compute the, like e to the minus x squared from 0 to 2. Yeah? So e to the minus x squared is like, so e to the 0 is 1 like this. So this will be something like this. From 0 to 2. And how to do it?
Count the squares.
Huh?
You count the squares.
You? Sorry, what's the question?
Count the squares.
Count the square. So what is the square?
No, you draw the truth table and then you count the squares.
You mean the rectangles? Like this? Yeah? So, okay, so you count, you just, like draw rectangles, yeah? And then this one, so who compute this one first? Who's the first one who compute this area in history? Huh? No, before Newton. I think before Gauss. Gauss after Newton. Archimedes, yes. So this one was computed in 232 BC by Archimedes. Okay, so and what he did was like this. He just divided into rectangles. Yeah, and then you just approximate the area on the rectangles and take the limits. Okay, and so this one, you know, the ideas was revised again by Riemann. So you know that this one under Riemann sum. Yeah. Right. So you just approximate by a collection of rectangles. Yeah. So f of xi, delta xi, I from 1 to n, and you just take n bigger and bigger, and then you approach the limit of the area under the curve. Okay, so numerical integration is exactly the idea of, you know, like approximate the area under the curve. Okay, but now we look a bit more closely. Yeah, so now suppose now I just so by the way, before we do closely, let me say that, you know, I mean, this one gives rise to this definition. Okay, the quadrature rules. So quadrature rules, it just, you know, if you, this one is delta xi, yeah? So delta xi is just the width of the rectangle. So if you label this delta xi, the width of the rectangle to be wi, okay, then you have this formula. So the area, yeah, so the area under the curve. So I from 1 to n, okay. So then this one we call it a weight. Yeah, so just give the definition, so this is a weight. And this one we call it the quadrature points. So this one is xi, yeah, so xi, so it's called a quadrature point. Okay, so that is exactly this definition. So we say that a quadrature rules, it's just any formula of this type. Okay, so the weights are w1 up to wm, and the quadrature points are x1, x2 up to xm. So those quadrature point is the point in the intervals. Yeah, and now we look closer to this formula. So now, well, so just wait, yeah. So now we look a bit closer to this formula. So now suppose I'm just like taking like only one intervals. So just forget about a lot of intervals. I just take one intervals. Yeah. Okay. So this one is A and this one is B. And my function maybe look like this. Okay. So now I just choose only one interval. Just choose one interval. Then, you know, the very first idea is we just approximate by the area of the rectangles under the curve, right? So approximate the integral f from A to B. It's just by the area of this rectangle. So this one is f of A. Okay. And now you see that. So now the error is just this difference. It's very big. So now how do you increase the accuracy with only one interval? So how do you make it more precise? So this one is use the rectangles, use only one rectangle. So now, so this one is the first method, right? So now I want another method that gives me a better approximation. So then what shape I should look for? Remember, we only one intervals, yeah? So I'm not going to divide it into n intervals. Just one. Huh? Trapezium, yeah. So I make it look like this. So it's a trapezium. Okay, so now this one will be f of A, f of B, and now the area look more closely to the area under the curve. So the height of the average height, yeah, divided by, so multiplied by b minus a. Yeah, so you have this one is a rectangular rule. So this one we call that a rectangular rule, and this one we call it a trapezoidal rules. So now what is the next step? So suppose I want to make it more precise, make it the errors, make it smaller. What? Only one interval. And what is the next step? Huh? Quadratic, yeah. So you see here you have a constant function, and here you have a linear function. So the next logical step is you use a quadratic. Okay. So if you use a quadratic, then suppose you have FA here, FB here. Then there's somewhere in between. Yeah, you have, so again this function look might be like this. Okay, so you approximate by a quadratic. So and now you have Simpson rules, yeah. So f of x is approximate by a area of the quadratic. So we're not going to be precise here. We will say what is a quadratic later. But this one was proposed by Simpson. Maybe Simpson. I don't remember what year. Maybe some year in the 19th century. And then we got it Simpson rules, yeah. So the ideas can be carried to a higher degree polynomials, right? Because this one is like degree 0, and then degree 1. Question?
Sorry, do you mind putting this one to focus? I don't know if that's possible.
Oh, sorry. Focus. Like this? Is it better? Yeah? So, but it's just a rough idea, right? So the rough idea that with one interval, you can increase the accuracy by increase the degree of polynomials. Okay, so initially you have degree 0, degree 1, and degree 2. And you see, you can go on degree 3, degree 4, and whatever. And that was proposed by Newton and Curtis. So, so now, in general, how do you know that? So in general, you can remember. So suppose you have a function from A to B, yeah. And now I want to so the function may be like this. Okay, so now I want to approximate the function by a polynomial of degree m. Okay, so this one is degree m. And, I want the function to be approximate by the polynomials, yeah, in a good way. Okay, so it's very reasonable to choose Pm to be the interpolation polynomials. Yeah, so you interpolate, so it means that you have to make. So now the idea is, now let me make the pictures bigger. Yeah, so now suppose I have So this one is my function again. Okay, and now you have m points. So you have x1, x2, x3, and so on up to xm. Okay, and now what you want is you want to construct a polynomials that go through those m points. Okay, so the polynomials interpolate the function, right? So I mean I skip a lot of points in between, so but assume that we have 4 points like this. Okay, so this one is Pm. Okay, and now if you remember the Lagrange interpolation polynomials, so Pm can be written as sum of fxi, lix, I from 1 to m. Yeah, so this one is the Lagrange form. Okay, so it will go through those points xi, fxi. Yeah, so it interpolate polynomials. So now your integrals, your integral f of x from a to b now will be approximated by the integral of Pmx. Okay. So instead of having the area under the blue curve, now you approximate by interpolation polynomials. I mean the area under the interpolation polynomial. So the area under the red curve. Okay. And now I just plug it in the formula. So now suppose I plug it in this formula, then I have, sum of fxi, lix, I from 1 to m, and integral from a to b. And you can see that because, the sum and the integrals, commute. So you can take the sum outside and the integral of lix, and fxi doesn't depend on the integral, so you just take it outside like this. So I from 1 to m. Yeah. And then this one will be the weights. And okay, so the weights will be given by the integrals of Lagrangian over a to b. And this one is the Newton-Cotes rules. So more or less, this one is just a generalization of the process we had before. So before, you had the straight line. Yeah, you have a rectangular rules. Then you have a linear function. Then you have a trapezoidal rules. Yeah. And then you just replace by quadratic, then you have Simpson rules, okay? And you can move on to degree m. Then you just have a Newton-Cotes rule. Yeah? And the weights can be computed explicitly by the integral of the Lagrange function. Okay? So maybe let me make it more precise. So go back to the formula. Okay, so now, so this one I approximate f by this interpolation polynomials in a Lagrange form. And this one is the exactly what I wrote down over there. And now, your exact integrals is approximated by this integral of the Lagrange polynomials. And you see the weight here is just the integral of the Lagrangian. Yeah, so the weight is just the integral of Lj from a to b. Okay, so now, suppose I want to do something concrete, then I have to, set m, say m equal 1. 2 and 3 and so on. So if I choose m equal 1, then what do I have? So suppose I choose m equal 1. So m equal 1, yeah? Then what is the Newton Quadrature rules look like? So you have A here, you have B here, and actually I choose the point x1 to be the midpoint, so A plus B over 2. Okay? Then, so remember we have the Newton rules, it's just the sum of f, xi, wi, I from 1 to m. And now because m equal 1, so you have only f x1, yeah, w1, okay? And x1 in our case is just f of a plus b over 2. And what is the weight? So the weight is just the integral of the Lagrange function. And what is a Lagrange function in our case? So now because we have only 1 point, yeah, and only 1 point, then the Lagrange function is just identically 1, yeah. So it just integrates 1 from a to b, because through 1 point, the Lagrange is just a constant, so 1, and you have b minus a. So therefore, in this case, you recover this formula. And what it does is, suppose your function is like this, then it just take the value at the midpoint and then compute the area of this rectangle. Okay? Yeah? And now, what happens if I take m equal 2? So what happens if I take m equal 2? So m equal 2 is I have 2 points, yeah? So now I take the first point is A, and the second point is B. Okay? And now my quadrature is f of x will be sum of 1 to 2, yeah? So it will be f of x1 w1 plus f of x2 w2, and f of x1 is just f of a integral of L1 x dx a to b plus f of b L2 x dx. So what is L1 and L2? So remember, because now you have 2 points, so the L1 is just x minus everything except the first point, yeah? So x minus b over a minus b. And L2 will be x minus everything except the second point. So x minus a and b minus a. Yeah? And so then integral of L1 from a to b is just, well, you have 1 over a minus b, just the common factor, the factor we don't have to worry about the integral. And then you integral x minus b. So integral x minus b will be x minus b square over 2, integral from a to b, from a to b, x equal a to x equal b, right? So then you have 1 over a minus b, and then you have 0 minus a minus b square divided by 2, yeah? And which is just, so you have a minus here, so the minus can go outside here, so it becomes 1 minus b minus a here. Then this one is b minus a square. So it will be b minus a. Okay? If my calculation is correct, yeah? And then you can do the same for integral of L2. So integral of L2 will be 1 over a minus b, b minus a, yeah? b minus a. And x minus a, so will be x minus a square over 2. X from a to x to b, yeah? And then this one is 1 over b minus a. And if you put b here, you got b minus a square over 2. And I missed number 2, right? Should be 1/2. Should be 1 over 2 here. Yeah? So should be 1 over 2. Okay? So this one gives you b minus a over 2 as well. And then when you plug it in here, then what you have is just integral of f of x is approximately, you plug it in here, right? So you just got f of a times b minus a over 2 plus f of b minus a over 2. And this is exactly the formula for trapezoidal rules we said before, right? So what is the point here? The point is the general mechanism can be used to recover the special case. Okay, so you see that we recover the rectangular rules when m equal 1. Okay, so just the value function at the midpoint multiplied by b minus a. And then after that, when you put m equal 2, you can recover the trapezoidal rules. Okay? So this general mechanism can be used to recover the trapezoidal rules. So this one is the calculation. I did it again here. But this one is very quick, but essentially the same. Okay? And now, you can do the same for m equal 2. So m equal 3. So this one is trapezoidal rules, yeah? So this is the pictures. So these are pictures of a trapezium here. So you can do the same, it's a bit lengthy calculation, but you can show that when m equals 3, you choose x1, x2, x3 to be 3 points like this. The left, the right, and the midpoint. Then by the calculation, of the Lagrangian, you can recover the Simpson rules. And this is exactly, like we discussed before. So we approximate the integrals by the area under the quadratic that interpolates the function at 3 points, at a, at b, at the 2 ends, and the midpoints. Okay, so I just skip this calculation. It's a bit lengthy, but it can be done. Yeah, so it's a Simpson rules. And so there is a relationship between midpoint trapezoidal rules and Simpson rules. So you can see that by just comparing the 3 formulas, Simpson rules can be recovered by the linear combination of the midpoint rules and the trapezoidal rules. Yeah? So now we move to another new definition. So now, we measure the errors between the exact integrals and the quadrature. Okay? So we measure by just taking the exact integrals minus the quadratures. Okay? And then we say that the quadrature rules has degree of precision R if the errors of the constant function 1, the error of the function x, up to the errors of x to the r equals 0. Okay? But when you raise the power to r plus 1, then the error is not 0 anymore. So, in other words, the integration can integrate those function 1x, x2 up to xr exactly. Right? Because when the error is equal 0, it means that you can integrate exactly. Yeah? So we do one example. So now just look at the definition, okay? So now go back to the midpoint rules. So what is the degree of precision of the midpoint rules? So degree of precision, So you have integral of 1, yeah? So this one is e of 1, yeah? From a to b minus the quadrature. So quadrature of 1, okay? Okay, from midpoint rules you have only from 1 to 1, yeah? Because, so if you remember, so this one is a midpoint rules, yeah? So only 1 to 1, yeah? So 1, m equal 1 to 1 of the function 1, yeah? And what is the weight? So the weight in our case is just b minus a, okay? So this one will be just b minus a, yeah? So what is b minus a multiplied by 1? And you can see that the first one, the first integral just b minus a, the second one is just b minus a, so just give you 0. Okay? And now the second calculation is what happened to e of x. So then you have integral of a to b of x dx minus b minus a, and now the function is x, yeah? So before function is 1, but now the function is x. So should be from where to where? So x at a. So sorry, it will be f at a plus b over 2, yeah? So it will be, so the function f equal x, okay? Then as at a plus b over 2 just equal a plus b over 2. Okay, because the function now f of x equal x, right? So therefore f of a plus b over 2 is just equal a plus b over 2. Okay? And now this one you just plug in calculation. So this one become x squared over 2 from a to b and minus b minus a, b squared minus a squared, right? Over 2. Okay, so this is a formula. B minus a, b plus a, just b squared minus a squared. And this one is b squared minus a squared over 2 as well. So then this can give you 0. So the midpoint rules, you know, e of 1 equals 0, e of x equals 1, e of x equals 0, right? And now what is e of x squared? So e of x squared is you do the same but for x squared. So integral from a to b minus, so the weight now will be, b minus a, yeah? But the value, so the value now will be a plus b over 2 square. Yeah? Because remember now the function is f of x squared. Yeah? So because here f of x equal x squared. So f of a plus b over 2 is just a plus b over 2 squared. Okay, and now this one will become 1/3 and x cubed minus, b cubed minus a cubed, yeah, minus b minus a plus b squared. And you can see that this, the last expression here in general is not equal 0. Okay, so in general, not equal 0. So then I say that degree of precision of the midpoint rule is just equal 1. Yeah, by definition, you can see that, you have E1 equals 0, E of x equals 0, but EX squared is non-zero. Okay, so therefore, degree of precision is just 1. For the midpoint rules. Okay? And there's a consequence of this statement, I mean, if you take a linear combination of 1x, x squared up to xr. Question? Any question? Or? No question? Okay. Then the errors will equal 0 as well. Okay? See, we just did this one. So the midpoint rules, the degree of precision is 1. Yeah? And now, I think I have an exercise for this one. So, degree of precision. So now I have a question for degree of precision. So now if you go to those, you can work on this. So now suppose that you have a quadrature like this. Okay? Then what is the degree of precision of this quadrature? So is it 1, 2, or 3, or 4? So just work on this one. So do something, otherwise you will feel asleep, So degree of precision. So somebody said it's equal 4. Somebody said it's equal 3. Just like a random number. Now you have to do some calculation, okay? I mean, this one, you just not, it's a multiple choice, but you have to do some calculation in order to show the degree of precision is something. This one is not a majority vote. So majority is, say, 2. So you have to do some calculation, okay? I mean, so we do some calculation for this quadrature, yeah? So now suppose you have QF. By the way, this one is one of the exam question in the past exam paper, okay? So suppose you have a quadrature like this. F approximate the function f from, so integral of f is the integral from minus 1 to 1. Okay? So now in order to find the degree precision, you have to compute the errors. Yeah? So the errors will be integral of f minus the quadrature of f. Okay? And now you have to put in E1. So E1 will be integral from minus 1 to 1, yeah, minus quadrature of f. So now you apply the function 1 here. So you have to 1/3, and then you have 1 plus 4 times 1 plus 1. Okay? So this one gives you 2 minus 6 over 3, which is just 2 minus 2 just equals 0. Okay? And now, so no majority, no. Okay, so let me do one more. Yeah? So Ex will be integral of minus 1 to 1 of x dx. Okay? Minus the value. So because f of x equals x, so at minus 1, it equals minus 1. At 0, it just equals 0. At 1, it just equals 1. Right? So integral of x from minus 1 to 1 is just 0 because of the odd function. Yeah? And so this one is minus 1 plus 0 plus 1 is just equals 0. So 0 plus 0 equals 0. Yeah? So degree precision is at least 1. Right? So we have 21% here. Okay? Still, we have to do more. So what is ax squared? Not evenly. Okay, so now, you have to do some calculation before you make the correct decision. Okay, so now, suppose I take x squared, right? Then this one will be my minus 1 square. This one is 4 times 0 square plus 1 square. And so this one, integral of x squared from minus 1 to 1 is just 2/3. And this one gives you 2/3 as well, so give you 0. So at least should be 2, right? Yeah? And then now you compute x cubed. Then should be minus 1 to 1 x cubed dx minus 1/3, and then minus 1 cubed plus 4 times 0 cubed plus 1 to the cube. So this one, the first one is equal 0, yeah? Because odd function integral over minus 1 to 1. This one minus 1 plus 0 plus 1, so give you 0, so equals 0. So this degree should be equal 3, right? Yeah? So I have to do one more. So now x to the 4th is x to the 4th minus 1 to 1, 1/3 minus 1 to 4th plus 4 times 0, 1 to the 4th. So this one, the first one will be 2/5, yeah? Minus, so this one will be 1 plus 1, so 2/3. So not equal 0 anymore. So the degree of precision should be equal 3, yeah? So degree of precision, so E of 1 equal E of x equal E of x squared equal E of x cubed equal 0, but E x to the 4th is non-zero. So degree of precision of this quadrature equal 3. Okay? And we don't have a majority, we just have a 19%, you know. So majority is just 1. Okay, so you get the idea, right? So the idea is you have to So give a quadrature, you have to plug in the definition. You do some laborious calculation, and then it gives you the correct. And now I'm going to give you a okay, so this one is an example as well. Simpson rules has degree of precision 3. And, and actually, if you look carefully, this one is just Simpson rules with a special A equal -1 and B equal 1. Okay? And we just did that for a special case. Yeah? And this one is one of the past exam question. Okay? So if you got it, then you get 2 or 3 marks already for the final exam. Yeah? Okay? 2 or 3 marks out of 60. Okay? So just let you know, yeah? So in the exam you have like 60 marks. So anyway, so that is the example that shows that the Simpson rules have degree of precision 3. And now we conclude the lectures by a theorem. We are not going to prove it. When we have time, we can prove it in the next lectures. So suppose that you have a Newton-Cotes rules. What is interpolatory quadrature rules? With m points, okay? Then the degree of precision is at least m minus 1. Okay? If m is odd and the point is symmetric with respect to the middle of the intervals, then the degree of precision is m. So before, we are not going to prove it, but before, we talk about this theorem, let's see whether this theorem is true or not. So remember, for 1 point, for m equal 1, for the midpoint rules, then the degree of precision is 1. Yeah? So that's correct, yeah? So for 1 point is the first part, say at least it's m minus 1, so at least 0. But then the second part, say that if m is odd, so m is 1, and the midpoint is, because you have only 1 point in the middle, so it's symmetric with respect to the middle. The degree of precision is 1. Yeah? And then for the trapezoidal rules, how many points you have? You have 2 points. Yeah? And trapezoidal rules, you can show that the degree of precision is 1 as well. Okay? In the previous, so trapezoidal, we didn't do this, but you can show that is degree of precision is 1. Yeah? So that's correct. Yeah? And then for 3 points, okay, so the Simpson rules. So you have 3 points. So that's odd, yeah? And 1 point in the middle. So it's symmetric. With respect to the midpoint, the degree of precision is 3. So the theorem is correct, at least for all the rules we have discussed in today's lectures. Okay? And then if we have time, we can prove this theorem in the next lectures. And I think we finish here, yeah? And see you in the lab. Okay, so if you have a test today,
everything is on labs or everything up to the end of chapter 5?
everything up to chapter 5.
So like secret methods and
Yeah. Okay. Yeah. Okay. So please email me. Yeah. Okay.